So we start our fourth day of the workshop with Boaz Nadler. We'll talk about robust sparse covariance estimation.
Thank you very much, Andrea, and thank you, Elias, and the other organizers of this workshop. It was very interesting so far. I'll tell you about joint work I did with John Goes and Gilad Lerman, who's here somewhere in the audience. And it is about combining high dimensions, sparsity, and robustness. And I'll be very specific about what type of robustness we mean here. So the talk outlined a brief introduction about covariance matrix estimation. I'll then review some prior work, which essentially assumed the Sub-Gaussianity. And then I'll present some results when the data comes from an elliptical distribution, which may be heavy-tailed. Okay. So suppose we have a p-dimensional random variable, and we observe data. And of course, we know that, in principle, all you wanted to know about x is found in its density. The problem is that we have curse of dimensionality. Estimating f would require, non-parametrically, in general, would require an exponential number of samples. And therefore, we typically opt to compute simpler quantities like the mean or the variance or other quantities. And many statistical tasks only need these lower order moments. So we have the mean, we have the covariance, we have its principal components, which are the leading eigenvalues and eigenvectors of the covariance matrix. And this is widely used for many tasks, for dimensionality reduction, visualization, denoising, in regression, classification, etc. And of course, if we observe data, we can replace the mean by the sample mean, the covariance by the sample covariance. And if we're interested in principal components, we do an eigendecomposition of our sample covariance matrix and use the estimated eigenvectors as our principal components. Okay. Now, in the good old days, we had data sets that had small dimension, large sample size. Also, the asymptotic analysis was done with p-fixed, sample size tends to infinity. And under various mild conditions, you get asymptotic consistency of all of these quantities. Errors behave, well, actually, there should be a squared here. But errors behave like p over n. And again, if p is small and n is very large, we're doing fine. But in high dimensions, so p over n is not small anymore. And in addition, let's say if p over n is larger than 1, you have more dimensions than sample size. Your covariance matrix is not even invertible. You incur an error which is at least as large as the smallest eigenvalue of sigma and much larger in general. And one question that has attracted the attention of the community is, can we do better under sparsity assumptions? And if we assume that the mean vector is sparse, this goes back to Donohue and Johnston and others. And there's a well understood theory about it, the sparse normal means problem. For the covariance matrix, both Bicken and Levina and El Karoui and many others around that time both proposed models for a sparse covariance matrix and proposed very simple algorithms, essentially thresholding, that were later shown to, maybe with some modifications, to achieve minimax lower bounds. Of course, there's also a lot of interest on inverse covariance matrices, and Peter Bullman and many others have worked on this as well. I'll not talk about this. I'll talk more about this in this talk. So, in particular, many prior works assume that a random variable x has sub-Gaussian tails. And we were interested in cases where x may be heavy-tailed. And again, the key challenge that is, I don't think, yet fully resolved is how to combine high-dimensional data with sparsity and with robustness to heavy tails, possibly also to outliers. I'll discuss this a bit at the end. So what I'll do today is discuss sparse covariance estimation under heavy tail data that specifically comes from an elliptical distribution. And towards the end, I'll discuss a little bit if we can relax these assumptions. Okay. So again, I'll discuss some theory, some algorithms, and there will be many open questions yet to be addressed. Okay, so here's the model that was proposed by Beacon and Levina. And there was, I think, a similar model by Nuruddin El-Karoui as well. We look at the covariance matrix, P by P, and we assume its diagonal entries are bounded by some number. And that when you compute the LQ norm of each row, it's bounded by some other number SP, which can grow in principle with P. And if Q is 0, then this is exact sparsity. If Q is 0, each row has at most SP non-zero entries. Okay. And the main result is that if you start from a sub-Gaussian random variable, p-dimensional, that has 0 mean, and a sparse covariance matrix, here's a very simple algorithm to try to estimate your sparse population matrix. You just compute the sample covariance, which costs you np squared, and you threshold it, which costs you order p squared. You just go over all entries, and you threshold roughly at this level, and you're guaranteed in spectral norm to have this arrow. And later on, Kai and Zhu proved that this is the minimax rate. So you have a procedure, very, very simple, that achieves the minimax rate. You couldn't hope for much better. Now, if you look at the result, why does it work? It relies on a very simple deterministic lemma, which says the following, that if you have a sparse matrix B, so here's our space of matrices, here's a matrix B, and it's approximately sparse, and if I have some other matrix A that is close to B in L infinity norm, entry-wise close to B, so here's my matrix A, and Aij minus Bij are smaller than some constant square root of log n over P. If you're able to find such a matrix A, then you can take a threshold with a case larger than this constant C, and you're guaranteed to have this result. Okay? This is a deterministic result. There's no random variables here involved. So why does this work with sub-Gaussian? Yeah.
So just one clarification. Take Q equals 0 and P proportional to n. Is it true that this is minimax or minimax up to log factors?
Wait. The minimax is not here. The minimax, this is the result.
Yeah, so what I'm saying is take Q equals 0 and
yes.
P proportional to n. Is there something hidden like a log P over S, or is really log P?
I think it's square root of log P over n. I don't remember if the results of Kai and Zhu are for Q larger than 0 or Q equals 0 exactly.
Okay.
All right. Now, so this is our target matrix. We want to get a matrix that entry-wise is close to it. And the reason why with sub-Gaussian data this is easy to do is simply that if you just take the sample covariance matrix with sub-Gaussian data, it satisfies this inequality. Okay? So this is essentially, I'm hiding all the non-trivial technical details, but this is the crust of the proof in the paper of Bickel and Levina, in other works. And Now the question is, what happens if we have heavy-tailed data? So this lemma is still correct. It's a deterministic lemma, but the sample covariance matrix will not satisfy this anymore. So we have to find some other way to get close to it entry-wise. And so one question is lower bounds. How well can we estimate a Sparse covariance matrix if we have heavy-tailed distributions? Can we do it in a computationally efficient way? And I'll show you some results when the data is elliptically distributed. So what is an elliptical distribution? It's a very common distribution in various fields, in particular in signal processing and communications. That's the definition. It has a mean mu. How do you generate an elliptical random variable? You start from a random vector eta uniformly distributed on the unit sphere. You multiply it by the square root of a shape covariance matrix, which is positive definite, and then you can scale it arbitrarily by a random variable u. And u is what gives you the heavy-tailed phenomena. You can take, if you take u to be Cauchy, then you have a random variable that does not even have a well-defined mean. Okay? Notice that this definition is not unique, right? I can multiply my shape matrix by 100 and divide u by 10, and I'll get the same result. So to have a precise normalization, of course, I'm aiming to estimate the shape matrix as P. I'll assume it has trace of P, which essentially means that on average, each variable has before the scaling by u, each variable has a variance of 1. Okay. All right. So, and so that's the definition of an elliptical distribution. And if the random variable u is sufficiently well behaved so that the population covariance exists, then it is a constant multiple of the shape matrix. Okay. And again, if you're interested later on in principal components, then of course the principal components of sigma and of S are the same. Okay? So here's the question that we're going to try to address. I observe n samples from a possibly heavy-tailed elliptical distribution, and I want to accurately estimate its shape matrix SP. I'm going to assume that it's approximately sparse. And I want to do it in a computationally efficient way. Okay. So again, the main idea is that we're going to try to construct some matrix S hat that would be entry-wise close to SP. If we're able to do that, we apply the thresholding and we're guaranteed to get the error rate that I had before. Okay. So first of all, remember, there is also this mean mu, which I also don't know. And if I'm going to have heavy tails, estimating it robustly may also be challenging. I think the next talk maybe will tell us about that. But I just want to get rid of it without needing to estimate it. And there's a very simple trick. It's a symmetrization trick. If you have two random variables that come from an elliptical distribution with some mean mu, just take their difference. It's still elliptical, but it now has mean 0, and it still has the same shape matrix. So I'll just look at n over 2 pairs, x2i minus x2i minus 1, and I'll recall. I'm doing some abuse of notation. That will be my n. So actually, I started from 2n observations, and now I have n mean-centered observations, and they're all elliptical, 0 mean, and shape matrix as P. Okay, and this idea appears in many papers. One of them is by Lutz Damgen. There he considers all pairs. I'm just taking n over 2 because I don't want to have dependencies in my analysis, but in practice you can use all pairs. So from now on, I'm going to assume that mu equals 0. Okay, so again, my goal, here is my shape matrix SP. And I want to find an estimator that is close to it entry-wise. Okay. Okay. So, regardless of sparsity, about 30 years ago, David Tyler proposed an estimator for the shape matrix of elliptical distributions, and it is the solution of this nonlinear system of equations. You have your unknown is your matrix sigma, and it appears on the right-hand side and on the left-hand side. And notice that essentially you can think about this as weights. So you have to suppose that there is a solution, etc. But suppose that there is a solution and it's unique, then the solution is essentially a weighted covariance matrix. Okay? Yeah.
Are these the first order conditions for some, convex program or something like this? Or I'm just curious.
So I'll discuss computational efficiency in a minute. Okay. Okay. First of all, this matrix, this nonlinear system of equations does not have a unique solution. You can scale sigma by any constant c, and it will still satisfy the equation. So Tyler suggested a normalization so the trace is 1, and Kent and Tyler proved if you apply these iterations, they prove that there is a unique solution under central assumptions, and that if you apply these iterations, it would probably converge to the unique solution. They don't discuss convex optimization. They just say, do these iterations and it will converge. Yeah?
Well, that's the question. It can also be phrased as, is there a family of distributions for which this is maximum likelihood?
Yes, so Tyler proved that Tyler's M-estimator is the maximum likelihood estimator of your shape matrix from an elliptical distribution. Yeah, so for the elliptical distribution, this is the maximum likelihood estimator. Okay. And you show that it's a robust estimate, it's consistent for p fixed and goes to infinity. And so, in principle, it seems that maybe, let's say that for a minute, p is smaller than n, then maybe computing Tyler's M-estimator and thresholding it may be a good candidate. Okay? Unfortunately, Tyler's estimator itself is not defined when p is larger than n. Notice the equation. On the left-hand side, you have sigma inverse, but you're summing at most n rank 1 matrices. So if n is smaller than p, there's no solution to this equation. And in the last 10 years, several people, mainly from electrical engineering, proposed a regularization approach. So without this term, you would have Tyler's M-estimator. They said, let's shrink to the identity. Okay. And people proved that if you take a large enough alpha, then this equation does have a unique solution. And this is called the regularized Tyler's M-estimator. People show that it has. So this equation now does not necessarily require any normalization. There is a unique solution for any sufficiently large alpha, and it satisfies this trace condition. And also, I think both of these works, which were published roughly at the same time, prove that, again, if you do these iterations, you will converge to the unique solution. Okay?
But
yeah.
So these are asymptotic results, right? Did they tell you at what rate you will converge?
This is, I'm going to address that in a minute. No, they just say, no, they just prove that these iterations converge. They don't have any rate. Okay? This is exactly one of the things I'm going to discuss in a few slides. Okay. So that so far was just a setting up the problem and a review of previous works. And now let me discuss our results. So again, here is our entry-wise thresholding operator. And if we have n larger than p, then we can try to compute Tyler's M-estimator and threshold it. I multiply by p because my shape matrix has a normalization that the trace is p. And for any values of p and n, I can try to compute my regularized Tyler's M-estimator. I'm going to remove the regularization term. I'll divide by the trace of this matrix, so I get a trace 1, multiply by p, so I get a trace p matrix, and now I'm going to threshold. Okay? So these are our two proposed estimators. And the result that we were able to prove is that this indeed works for elliptical distributions. We're thinking about an asymptotic model where n and p grow together, and we have a sequence of shape matrices that are approximately sparse. P over n tends to a constant. Here the constant has to be smaller than 1 because this is for Tyler's M-estimator. Then doing this would get you the same asymptotic error rate as the thresholding the sample covariance with sub-Gaussian data, and we've discussed that this is a minimax rate optimal. And a similar result holds for for the regularized Tyler's M-estimator, that with a sufficiently large regularization parameter, we get the same rate. Here, we need an extra condition that the largest eigenvalue of the shape matrix is bounded by some absolute constant. This condition does not appear with sub-Gaussian data, and I don't know if it can be removed. I'll explain where it comes from in a minute. Okay. So as we've discussed, these estimators are rate optimal. Okay. Okay. So I will not describe the proof, but only highlight some concepts about the proof. So in general, it relies on recent results from random matrix theory, concentration of measure, concentration of quadratic forms. And here are the key ideas. So first of all, let's go back to the definition of Tyler's or the regularized Tyler's M-estimator. Yeah, here's the equation. Notice that this estimator is invariant to scaling of individual vectors, right? If I take an observation xi multiplied by 100, nothing happens, right? You get 100 squared here, you get 100 squared here. It would have the same effect, okay? And therefore, instead of analyzing general elliptical distributions, I can assume that my underlying data is Gaussian with this shape matrix. That's the first step. The next step is to write the regularized Tyler M-estimator as something times the identity plus something else times a weighted covariance matrix. And the key idea is to show that these weights, when the data is Gaussian, that these weights are very close to being constant. Now, if they were all exactly some constant, like r over n, or some value r, then this would be the sample covariance matrix, and then this explains why the method works. Okay? So the key technical part is to prove this result, that with Gaussian data, all of the weights, even though you have a highly nonlinear equation for the Tyler's M-estimator, all the weights are tightly concentrated around some value R over n.
So,
Yeah.
so one thing that is not good, the weights depend themselves over sigma. So what do? You prove that the concentration holds uniformly over.
Yeah, excellent question. I have x1 up to xn. They have weights w1 up to wn. All the weights wi are all functions of all the xj's and on the shape matrix sp. Yeah, they are the solution of that highly nonlinear equation. Okay, and the value r, the limiting value r, is a function of sp, alpha, well, let's say p and n, but asymptotically it depends only on the ratio p over n. Okay, so that's right, p over n. Okay, and this is precisely where I need that extra assumption that lambda max of sp is smaller than some absolute constant s max, because I need to, or at least our technique currently needs to bound this r so it doesn't explode and that it doesn't go to 0. And this extra condition, which is not present in works that only assume the Sub-Gaussian data, this condition ensures that this limiting r remains bounded. Okay, that's how it works. Okay, so this is essentially the key technical part. Yeah.
But it seems to some extent that that should also be needed, because at the end of the day you need to guarantee that you are in some sense doing a fixed point iteration, so you need to have that the map is contracted, probably in this case under the operator.
Yes, I'll show that I'll discuss in a minute how the fact that you can compute Tyler's M-estimator in a computationally efficient way, but this is just tells you, regardless of how can you get to the limiting or to the unique solution, in the unique solution the weights satisfy this concentration of measure. Okay, other questions? Okay. So for Tyler's M-estimator, we use a result of Zhang, Cheng, and Singer from 2 years ago. And in their case, p is larger than n, and the limiting constant r is just 1. So wi's are roughly 1 over n. So with Gaussian data, Tyler's M-estimator is very close to just a sample covariance matrix. And okay. For the regularized TME, yes, R is a function of alpha, p over n, sp, as I wrote here more precisely. I need to show that R becomes bounded so things don't blow up, and this is where there are several pages of algebra that are needed to prove this. Since many people have asked me, can you compute this in polynomial time? So again, previous works about either TME or regularized TME, as far as I know, the result says start from some initial matrix, do these iterations, and you're proven to converge, but they don't give you a rate of convergence. What we were able to prove is the following result. So first you give me a data set, and I'll compute this number, I'll compute this norm. Again, I'm what do you call it? Roughly spherizing my data. I'm normalizing it and multiplying everything by p over n. So I'll compute this matrix, compute its spectral norm, and if you had what I'm going to tell you about now does not assume elliptical data, okay? But if you had elliptical data, then this number would be roughly 1 plus square root of p over n squared. This would be the largest eigenvalue of that's the edge of the Mochenko posture, essentially. And here is the lemma, that if you take a regularization parameter large enough, larger than, let's say, 5 times this quantity, then you get linear convergence rate with a factor of half. Okay, and you can play. You can change, make this smaller. This will be slightly larger, etc. So if you want accuracy epsilon, log 1 over epsilon iterations will get you there. And each iteration, you need to invert a matrix. So you can do that in minimum between n and p cubed operations. Okay. So I think this should answer your questions earlier. Okay. And another point I want to make is that it's computing this is practical. On a PC, it just takes a few seconds, let's say for 1,000 by 1,000 matrices or something like that. Okay. All right. Great. So I want to show you some simulation results. This is I'm missing an absolute value here. This is a matrix that also was Bickel and Levina had in their paper. I'm going to take this as my sparse shape matrix, and I'm going to look at 3 possibilities: just Gaussian data. I'll take Laplace, which is heavy-tailed, but moments exist, and then I'll take Cauchy. And I'll look with various values of p over n. And we'll look at the sample covariance, thresholding the sample covariance, looking at the TME, and then thresholding the TME. Okay? And we'll compute our error as mean squared error in the spectral norm, and we'll take a log. Okay. So this column is, so each row is a different p over n. And this column is just Gaussian data. And for Gaussian data, thresholding the sample covariance or thresholding TME essentially give you the same result. You don't see these because they're exactly on top of these. Whereas once you have Laplace data or Cauchy data, computing the sample covariance and thresholding it does not work, but thresholding the TME gets you small errors as a function of sample size n. Okay? All right. Now, I looked at what happens if I have outliers or a contamination model. So suppose that 1 minus epsilon n of your data comes from an elliptical distribution with a sparse shape matrix S, and the other samples come from a different let's say, elliptical distribution. Okay? And I'll take 2 different models for the outliers. In the first one, so the outliers have a shape matrix D. Well, and then it's rotated so that it's a non-sparse shape matrix. But one model is that the outliers are diffuse throughout the unit sphere. And then the other one, the outliers are essentially on a 2-dimensional subspace, right? There are 2 directions where, P and P over 2 where most of the outliers live on. Okay? All right. And so, for example, in the first example, S max of the outliers is bounded, and in the second one, it increases with P. Okay? All right. So, so we have data inliers and outliers. If somehow we were able to distinguish the outliers, we could remove them and recompute everything in threshold. And what have we learned so far? If we had only inliers and we compute the regularized Tyler's M-estimator, all the weights are very close to some value R. Okay? Which we don't know because we don't know the shape matrix, but we know that tightly concentrated around some value R. And the hope is that the outliers will have a different weight. If they have different weights, then we can easily distinguish that. and this is indeed, at least empirically, what happens. I sorted my data, so I had 500 points. Here I had 100 outliers, and here I had 200 outliers. And as you see, the inliers had some value r. The outliers had a different value of r. And now it's very easy to distinguish between the two. I just compute, let's say, a non-parametric density estimation of the weights, find the mode, take something around the mode, and then this is essentially, so the blue line is a non-parametric estimation of the mode, and this is a band of, I think, maybe one or two, maybe two standard deviations around the mode. Okay? So here's where we have some open questions and conjectures. So one conjecture we make is that asymptotically, if you have a mixture of inliers from an elliptical distribution and outliers from a different one, you would have the weight would concentrate around two values, W in and W out. For a different estimator, there is related work by Mackay and co-authors. Now, what happens in the, so this is a simple procedure to try to detect the outliers, okay? And this is what you get as a result. On the x-axis is your outlier ratio. This is your error without removing outliers, and this is the error that you get after outliers have been detected and removed. And you get your breakdown at roughly half, which is where you cannot distinguish between the two. Let's take the other case. In the other case, the outliers were on a subspace, more or less of dimension 2. That subspace had did not satisfy this condition. It increases with p, and what you see here is that the outliers now, instead of being concentrated around some weight, other weight r, they are all over the place, but that's fine. I can still compute the mode of all of these weights, a band around the mode, and this is what you're seeing here. And you can still remove most of the outliers. Of course, if some of the weights are in this band, they stay there. And in this case, it seems that the breakdown point is even better than half. Okay, because I don't have because these would even if I had 80% outliers, they would. Well, I didn't. Yeah, I don't see it here. I didn't. Yeah, even if you have more than 50% outliers, you would still get a similar picture. And it seems that in this case, you can do something even better. So again, this is without removing of outliers. This is perfect. Okay, you see, 2 slides and I'm done. All right, so some open questions. First of all, the results I presented were theoretical. The threshold, I'm just saying that even without outliers, the threshold, the statement says that there is a threshold, or for any threshold asymptotically, you'll get the minimax rate. How to estimate the threshold in a data-driven manner is an interesting question. Can you do the analysis if P increases with n at a higher rate than n, like n squared or some other increase? A rigorous analysis of an epsilon contamination model. I should mention here a work by Chen, Gao, and Ren, who's one of them is here at least, and they analyzed robustness to outliers using Tukey's depth function, which in general is computationally hard. And the question is there a computationally efficient or practical robust estimator for at least a certain class of outliers with, let's say, the inliers being, let's say, Sub-Gaussian or something else? So to summarize, and also maybe to distinguish, so Elias talked, and I think also Daniel, about robustness to outliers in high dimensions, but sample size also increases, maybe even larger than the dimensions. There are cases where the dimension is large, but sample size is limited, and we want robustness in that case as well, and then we also need to assume some sparsity. So I think it's a different regime, which is also interesting to look at.
So there are a couple of works on sparsity.
Okay.
But they do not yet work for these assumptions, like sparse Gaussian, but
Yeah.
not for these moment stuff.
Okay. What we've done is something in a way limited, but it's a first step, how to estimate a sparse covariance matrix using heavy-tailed data. I should mention that in ongoing work, what I told you about holds for a much larger class of underlying distributions. You can start from a random variable which is not uniformly distributed on the unit sphere. It only needs to satisfy a log Sobolev inequality, which is slightly stronger than Sub-Gaussian, but then you can scale it similar to an elliptical distribution. And everything I told you, we believe, continues to hold. We're still working on this. And again, I think an interesting question is there a practically computationally efficient method that can handle arbitrary outliers, or what type of outliers can we handle not only computationally efficiently, but something that is practical, that has runtime, I don't know, let's say p squared or p cubed or something along those lines. Another interesting question is if you want to do sparse PCA or robust to outliers. That's, I think, also interesting. There are various papers on my website. Our paper is on the archive. Thank you very much.
Any questions?
Two questions. The first one is, since you're dealing with elliptical distributions, could you just use something like a Kendall-Tal statistic to approximate the covariance matrix? Why use Tyler's method for estimating a covariance matrix?
So there is a paper by a group of Jenkins Fund from Princeton that I think they use Kendall's approach. It has some parameters that they also need to tune. We use Tyler's because it's widely used in various applications. It seems like a natural candidate, and it works.
And the other question is concerning Tyler's estimator. I think there's been some work on the fact that it's geodesically convex. So you could try to optimize the problem and try to estimate sigma hat by using some kind of descent method according to the geodesic convexity. Then you wouldn't have to do this iteration method.
So again, as far as I know, these iterations are the way people practically compute Tyler's M-estimator. And what we proved is that with sufficiently large regularization, it's strongly convex, if you wish. There is a linear convergence. Okay.
Other questions?
Do you think it is in any way crucial to have methods that are based on thresholding, or is there any hope of doing, some form of spectral sparsification or sketching? Are there
sketching is something else. In sketching, you subsample your data or you do something else.
Sure.
You lose information in a way. Thresholding has been found to be a universally excellent procedure to handle sparsity once you get a nearby estimator.
But is there a sort of a very strong reason for that, like from an analytical viewpoint, like where you really feel like you need to be doing thresholding as opposed to some other form of specification?
Well, any form of specification would, you could think about shrinkage that does not necessarily set things to zero. You can think about other penalty terms that maybe would shrink in a nonlinear way and not necessarily set things to zero.
Okay, there was one
Could you
question.
say again how your bounds are depend on S max? You require a bound that's bound S max, and then it's
yes. Excellent. I think so. The short answer is that Where's the, okay, the short answer is that this assumption implies that there is no constant here that depends on S max. But remember, it may seem counterintuitive.
So
P and
the
N
constant
P and N
doesn't depend on
P and N
S
go
max
to
or
infinity,
max.
and this is fixed. If you would allow this to depend on P, then you would have. Okay, got it. Okay, got it. Yes, you have something here that depends on S max or something like that. Yeah, but that's why I want it fixed.
Polynomially.
Yeah. Yes.
Okay. In the various simulations, you have to make some choices about alpha, the level of at which.
So yes, I took. Okay, so excellent. It turns out that in simulations, once you satisfy this, the results are very weakly dependent on alpha. Any alpha would do. Remember, I'm removing the. Before I do the thresholding, I'm removing this part. Okay. And empirically in our, well, both theoretically but also empirically in our simulations, there's no dependence on alpha, or very weak dependence on alpha.
So if you give me a data set, I pick alpha to be.
No, you should pick alpha to be at least as large. Okay, theoretically you would want it at least large of this. You don't know this, so just take alpha to be larger than what is it? Than this. Yeah, this is exactly what we did in the simulations.
And the thresholding, we used what value for threshold when you showed us your curves?
Wow, it's probably in the paper, but some constant times square root of log p over n. Doing that in a data-driven manner is an open question. Yeah.
Last question. I just wanted to check what, I mean, typically when you have a fixed penalty, let's say, for example, with the lasso and things like that, you get bias. The reason you don't here is because the shaping is invariant to scale, right? Right, because you bring in the alpha, the alpha I, you have a penalty.
Yeah.
Right? So
I'm not sure I'm following your question.
well, I mean, it's just really trying, it's a check on that. Why is it that you do not have bias in your estimation of the shape? And it's because
As a function of alpha?
yes,
I'm removing the part on alpha. Yes.
by scaling.
No,
No, by subtracting. The alpha is.
Oh, you mean the I see. Okay, that's what I meant.
That's the estimator, and I'm removing this part.
Then it's being removed.
Okay.
Okay.
Okay. Thank you very much.